Okay, so we decided to split it up in a way where we would each focus on one aspect to make it easier on ourselves. And I took asteroids because I'm pretty sure Brandon has a bit of background knowledge, and this was all kind of new to me. So he went with the moon. Um, and starting off, I think like the first thing, like the first step for us, well, for me, was just identifying what the images were, right? Because I did all the readings and we went through everything, and it gave a pretty good like sense of like how we were supposed to approach it. The first image here is the asteroid Itokawa, and it was retrieved, like its samples were retrieved from Hayabusa. It was a 2010 mission, and just based on like initial sampling and stuff, we know that it's a chondrite, and the spectral type is S. Just looking at the asteroid, we can see that it has smooth and rough surfaces, and it has a layer of regolith, which is estimated to be like a few 10 centimeters. The observed particles of this asteroid are very fine. They're like centimeter-sized pebbles concentrated on basically smooth terrains, and they lack like the asteroid lacks smaller craters, and this is possible evidence of seismic activity. And the larger boulders seen throughout Itokawa is like debated. The evidence behind it, or like why we see that stuff. And one of the theories is the Brazil nut effect, which is kind of like if you have like a can of nuts and you shake them, then they would vertically align. So, but the evidence on why the large boulders are like it says here, like it's very debatable. Like it's not concrete yet, but that's just like what I got just based off like observations. If we take a deeper look into the surface processes, we can take a look onto a couple of different things. The first thing here is like shape distribution. So when the scientists did a lot of complicated calculations, but based off those calculations, we can understand a lot about the history of the asteroid itself. So in respect with the three axial ratios, the fragments were formed were similar to those that scientists have made through high-speed impact labs. And this shows that the Itokawa particles probably developed from mechanical disaggregation. When the particle size distribution was calculated, it had a log slope of like -2, and this indicates that it's more gradual than that of boulders. And this was also consistent with close-up of regolith taken by other areas in the Hayabusa mission. The smaller particles are probably due to the higher ejection velocity and the higher loss rates that were observed. Surface modifications on the asteroid include these space weathering rims, which are basically thin layers of silicates containing the iron-rich particles. And then the nanophase darkening has to do with the reflectance spectrum. Another important aspect of like the surface of Itokawa is the grain abrasion of certain particles. We see that like the particles have these angular edges, and this shows us that they're probably mechanically crushed rather than eroded almost. And this has been proven through high resolution FVSEM techniques. But the specific type of weathering on Itokawa is a little specific to the asteroid itself, and it should be known better as space erosion. The abrasion itself is a result of grain migration, and that's probably due to seismic waves repeatedly reflecting off the surface post impacts. And then solar noble gases from the particles are consistent with grain motion. So we know there's a lot of movement happening within the regolith layer, and that this is also connected to the space weathering and the silicate layers. Things that aren't known about Itokawa, and some of that is like the absolute formation age, that's still uncertain. We're not 100% sure about that, and the nature of the impact. So we know certain aspects of the parent body, but it's not like we don't have the complete picture yet. And what we do have an idea of is like the type of asteroid it is, probably where it is in the asteroid belt, which is just given to us by its class, and kind of like what the particles that we see is what they show us. So that was all for image one. And then image two is this antique, is known as antique Vesta. And Vesta is like the second largest asteroid that like is really, really important to like asteroid and moon scientists basically. It's it's like a single differentiated rock body, which makes it a lot different from other asteroids because they're usually like together. There are a bunch of particles fused together. It's covered with regolith. It has a bunch of igneous rock, hundreds of craters, and it has a very significant basin at the South Pole, which I talk about later. It lacks lava flows and it has a lot of volcanic constructs, and there's an abundance of steep slopes. So chronology and impact history regarding this one is that it's approximately 3 to 4 billion years old, and this we just know from observing the craters. And then the 4.5 billion year crystallization of eucrite reveals that Vesta probably melted and differentiated even earlier than that. Around 4.1 to 5.4 billion years ago, we can predict that it was probably struck by massive bolides. And this period when this happened is known as a high impactor flux or a late heavy bombardment period, which is basically when a bunch of massive careening bodies like come together, they crash, it's very catastrophic. And the result of this is gravitational starting within the asteroid belt. So this all is revealed through the number of peaks that I mentioned before that are present on Vesta. And there's like a bunch of eucrite breccia known, which is all indicative of like age in asteroids. The basin I was talking about earlier is known as Silvia, and it's about like 1 billion years old. It's the most like visible aspect of this specific asteroid, and it was determined through crater counting. The age of this one is specifically consistent with other types of asteroids as well, and its impacts, like the original theory is that the impact should have destroyed Vesta. Looking at the base and the size of it, how powerful it was, but the metallic skeleton it has could have helped it survive. The effects of it are very significant though. There's like a bunch of ridges, troughs, and a lot of like on the equator specifically. So overall, the asteroid is very rich in surface processes, but the most like significant one would have to be the basin near the southern pole. And then we can look at Vesta at a more geographical approach. You can see that there's a lot of igneous rock-based regolith, which I kind of mentioned earlier. There's also meteor link evidence, which is important because it's identified that Vesta is probably the parent body of a bunch of other meteorites, and this can be seen through analyzing the composition of different materials and matching them. So we know that igneous howardite, eucrite, diagonite, or HED, meteorites are based off of this asteroid because of their spectral similarities. These type of, or diagonites are these types of rocks formed through accumulation of crystals, specifically olivine and pyroxenite. And oopsie, I'm sorry. And the similarities between the two is what allows researchers to make these connections between parent body asteroids and the meteorites connected to them. Another way that we can understand the surface is through reflectance spectras. The greatest concentration of the pixels when reflectance spectra like calculations were done corresponded to the howardite and the eucrite. The howardite to represent the regolith on the surface area of the asteroid, and there was another very significant discovery is hydrogen within the regolith. The fact that Vesta's surface is covered with howardite can also help us make connections with other meteorites, which we find that have similar compositions. The last thing we can touch upon with this specific image is space weathering. So bombardment and like impact has caused lunar soil, which is like a process derived from space weathering. And the albedo, or like the brightness of the surface of Vesta, has been exposed through impacts. And this changes over time. So like the albedo has been changing over time, but as it like exposes certain things, we can tell, we can understand further about the process. So we also know that Vesta's location is far from the sun. So when impact velocities are lower, um, there's a possible shielding of cosmic radiation, and this can account for the difference in soil mineralogy because of like we know like how I discussed earlier, there was this period of bombardment, right? And this caused these like asteroids to undergo specific weathering, but sometimes like there's inconsistencies, and those inconsistencies can be accounted for based on location, how far the asteroid is from the sun, or where it is within the asteroid belt. And then the last image that we had was 433 Eros or Eros. So Eros is an S-type asteroid. It's part of the Armor group, and it's it's on the Mars side of the asteroid belt. It also consists of a layer of regolith, but the main, I think, difference here is like fine dust. And there aren't as many craters on this one, but there is evidence of seismic activity. It has a very low gravity environment, and the depth of the regolith is around 10 to 100 meters. And this one is known to be known to be similar to Itokawa. Spectral variation was very important in understanding the space weathering for this one. And also for this one, I'd just like to point out, like, there was not a lot of information in like the PDFs that were like assigned, right? But if I went on the website and I just searched in Eros, and it gave me a bunch of information, and the studies that were done use spectral variation, which is where I'm getting this information from. So Eros has no evidence of like heterogeneity. So there's significant spectral variations between them, and this was found through a very specific process. So basically, they cut the extended spectrum data set into subsets, which were based on a bunch of different factors like geography and geology and certain crater locations. And then they comprised some of the darkest one and some of the most weathered ones, and they averaged them. And so when we look at the most bright to dark spectral ratios, they're consistent with space weathering in the lab. When we looked at the ratio specifically, that gave us evidence for space weathering on the surface of Eros. The freshest appearing materials are like around the rims and walls of Himeros, which is one of the indicated locations in the study. And the other craters could be like a more weathered surface, or the average part of Eros. The brightest materials are also representative of unweathered pristine materials and like a more uniform body. And this is all derived through like spectral parameters for Eros. The evidence shows that it's consistent of being an S4 asteroid with a very low iron composition. It's probably thermally metamorphized, and it's an ordinary chondrite. Overall, this specific asteroid was the one that's most similar to the first one I discussed. And just comparing the two, we can see like a bunch of similarities. So if we look here on the Eros side, the first like 3 bullets, the fact that it's an S-type near Earth asteroid, its composition is consistent with ordinary chondrites, and that it's a product of catastrophic disruption, is all the same in Itokawa. Like, these are the similarities between the two. When we look at the differences though, it's more about the specific surface processes that we're seeing and why they're there. So Eros has very linear structural features on the surface, and this indicates that it's more globally consolidated. Like, it's not as rough, it's more put together. And it's inferred to be a collision, like that, like inference. And this has been shown through the twist and through going fracture. And such processes are observed on such a scale that they probably formed from a parent body, right? And there's also evidence of mass motion on regarding the regolith on Eros, which is probably like in the form of debris flow. More recently, though, it's been stated that Eros is not a rock shard, but more like very fine-grained, cohesive type of rubble pile. Because if we look on this side, the major difference between the two that was that like Itokawa is known to be a more like rugged rubble pile type of asteroid, whereas Eros was supposed to be like a shard. But more recent discoveries actually also a rubble pile. It's just more fine grained. And then the last like major differences with Itokawa are that the formation of certain fragments is probably due to a catastrophic disruption event, and that the crater and boulder populations, they're inconsistent with like a collisional shard type of formation. So it wouldn't be similar to Eros in that sense. Composition wise, both mineralogically and elementally, it is like Eros. It's consistent and it's like an ordinary chondrite, but the density lower. There's also an absence of global fabric, which is very prominent in Eros. Like that's what makes it very different from the other one, and it's just not present in Itokawa. And there's a very large population of these blocks, which are much larger, right, relative to blocks that could have possibly been found on Eros. And Itokawa has a lower crater population. Regolith, which is like the main thing that we usually look at when understanding surface processes. On Itokawa, it's very globally segregated, and there's this like thing where certain scientists believe that there could be these like giant ponds, whereas Eros, it's very fine-grained, put together, it's smooth, has a lot of more surface processes and figures that give it a bit more complex. I think that's it. So overall, Eros and Itokawa were the most similar ones. Of course, they had their differences. Second image, I think, was overall the most different. Thank you.
Okay, thank you. So I learned a lot. I just say you totally went a lot farther with this than you really needed to, but that's okay. That's okay. Did you enjoy it? Maybe
Yeah.
did you like diving a little deeper and trying to find more?
Honestly, like if I didn't really know like how far we were supposed to go, right? And I just kind of wanted to make sure I had evidence for everything I was saying. So it took me a while. Like not everything was there. Like I looked through your website, which was super helpful because then I found specific studies, but it was actually really interesting. Like I haven't done like space and earth science type stuff. So it was like a nice change.
Okay. Yeah, asteroids, with a few exceptions, aren't particularly geologically interesting. Unless you like dealing with very small particles, like unless you're a sedimentologist or something. But when you start talking about reflectance data and compositional data and like trying to compare them to meteorites, then they get more interesting. But in general, and it's interesting because I never really bothered to learn much about meteorites because they kind of scared me, I guess, because there's so many of them and they just seemed very confusing. Just lots of different types and whatever. So I just kind of ignored them. But I mean, I now totally understand why they're important and the significance behind them. I don't really have any questions. I did have a question though. One though, I guess, for Eros. If you go back to your first slide, we were talking about Eros. Is that bottom right image from Eros?
Yes. But
Okay.
it's not one of the ones you guys provided. I did like a Google search just to get
Right. And I think that image on the upper left is Itokawa. It's just the other side of it, I think. It may be
yeah,
inverted.
I thought that too, but when you like look it up, that's one of the ones that came up. So I wasn't like 100% sure for that one, but
what do you remember what web page you found it on?
I have it somewhere else. I could find it for you.
Okay.
I
Well,
just
it's okay. Because Eros has a very looks like a bone
okay.
type of shape
Most
to
of
it.
the images I remember were more close up. Like I was trying to find one that was like more spanned out, but I think it was probably like I probably got confused.
That's okay. No, I'm pretty sure that's an image of the other side
of
of
Itokawa, right? Yeah.
Itokawa. Yeah, because Eros has a shape like it's like a bone, but you can actually see craters on it.
Okay.
Even on a large scale, you can definitely make them out. Anyway, Okay, very good, very good. Let's go ahead and go to our lunar presentation. Thank you, Miriam.
All right. I'm just waiting for the menu thing to go back up. All right. So first image I did, for all the 3 images, I did like a general overview of the whole thing itself, and then I focused on specific features of the image. So with the first one, the main surface features were really just impact craters. This area is located in one of the mare on the moon, so all the rocks are mainly basaltic because they're all volcanic rocks. And I labeled 5 craters here. So the first crater, I just want to point out, it's kind of interesting because you have the Apollo 12 landing site and the Surveyor 3 landing sites here. So the crater is 150 meters in diameter, which I got from the scaling of the original image, which was 150 meters. This one I found to be the second oldest of the 5 craters that I labeled. And I found that because it's clearly not as old as crater C, but it's more defined than all the others that I labeled. It has ejected material inside it and has had a lot of other impact craters inside it, which led me to believe that it was a lot older than a bunch of the others. So crater B, I found to be about 90 meters in diameter, and it was the 4th oldest in this image. And it looks like it has a similar age to crater E, but I wasn't really sure if it was older or not as old as crater E. I just said that they were similar age. This one is a complex crater because you could see a central peak in the middle, but it's the simplest complex crater. This is formed when the impact is so great that the energy from the impact causes the inside of the crater to collapse in on itself, and then that forces the center of the crater upwards. It has also been filled partially with ejected material from surrounding impacts and has had a couple other impacts inside it. Crater C I found to be 190 meters in diameter, and it's oldest of all 5. I realized this because it's the least defined of all the 5 craters I labeled. It has the most ejected material inside it, and it has the most craters inside it. Crater D, I think is a complex crater because it looks like there's a little bit of a central peak, but I wasn't too sure about it. I found it to be 10 meters in diameter. It's the newest of the 5 craters that I selected because you could see the lighter ejected materials surrounding it. And crater E, I found to be 100 meters in diameter, and the third oldest of the 5 craters that I labeled. But like I said, it's similar in age to crater B, so I wasn't really sure. So image 2. So this one has really just impact craters, but it also has a straight ryle. It's the landing site of the Apollo 15 mission, and it's also located in one of the mare, so mainly basaltic rocks from volcanic eruptions. So surface feature A is a straight ryle that's about 1.1 kilometers across. This one formed, I believe, from, I'm not sure if it would really be considered tectonic plates, but something similar where the surface of the lunar surface is kind of pulling apart, which formed a mountain range, which you could see in the next image. So I believe it's the second youngest of the features that I labeled here. And I decided that because there's very few impact craters inside it. Surface feature B is a simple impact crater that's about 30 meters in diameter. It's the youngest of the 5 because you could see the ejected material surrounding it. And it's really clear compared to the surrounding area if you look at it here. So feature C is an impact crater that's 700 to 800 meters in diameter. It's the oldest of the 5 labeled features because it's the least defined. It has a lot of ejected material inside it and a few impact craters. Feature D is also an impact crater, 180 meters to 200 meters in diameter. I think it's a complex crater because I think there's marginal collapse over here. And I think it's the second oldest of the 5 labeled because it's less filled in than crater C, but it's less filled in than crater C, but more than feature E. And feature E is another crater that's about 80 meters in diameter. And I think it also has a central peak here, but it's hard to tell like one from the last image. It's the third youngest of the 5 labeled features. So image 3, I think this is actually the same area that image 2 is taken from, just a wider view. So where you can see this Ryle here, that's the same one from the last image. It's called Hadley Ryle, and it's in the Montes Apenninus range, which is the landing site of Apollo 15, like I mentioned before. The mountain range is 3.9 billion years old, and it's also located in a moraine of volcanic rocks and basaltic rocks. So I just started out with feature B because it would be easiest. So this is Hadley Ryle. It's the same one as the one that I mentioned earlier. It's about 1 kilometer across, and it's a V-shaped Ryle. So I am confident that this was formed from this lunar surface pulling apart, because surrounding it you have this mountain range. So when this mountain range formed, this Ryle also formed from the surface collapsing in on itself. I think it's the third oldest of the 5 labeled features in the image. So surface feature A is an impact crater about 5.6 kilometers in diameter. It's a simple crater, and it's probably the cleanest of all the craters that I analyzed in the 3 images. It's been partially filled in with either ejected material or some of the material that's on the rim of the crater or just on the edges of it that fell down. And I believe it's the youngest or second youngest. Similar to the last image, I wasn't sure with feature D because they can't really be compared to each other because they're too far apart. And you can also see it overlaps over the Ryle here, so it definitely has to be newer than it. Surface feature C is the mountain range that I mentioned earlier. Its highest peak is 5,400 meters, and it's about 600 kilometers across. So when this mountain range formed, it also formed Hadley Ryle here. And I think it's the oldest of the 5 labeled features because it's covered in other impact craters. Surface feature D is a simple impact crater. It's about 500 meters across. It's clear that it's simple because there's been no modifications. It's similar to feature A. It's really young compared to the others, and that's clear because you could see ejected material that's lighter than the surrounding area. But I'm not sure if it's older or younger than feature A because they're just too far apart to really tell. And surface feature E, it's hard to tell if this is 2 or 3 craters, but it's about 1.7 kilometers in length. I believe this is formed because an object came in at such a shallow angle that it spread out across the surface when it hit. Because when impact craters are formed, they're not really formed from the impact itself, but they're formed from an explosion that happens from the amount of energy when they collide with the surface. So if it wasn't at such a shallow angle, they would just appear like regular circular craters. And I believe it's the second oldest of the 5 labeled features. And this is kind of off topic, but the study recommended that I shared with you a couple pictures from the lunar eclipse recently. So I just have a couple here. because it's the moon. And that's it.
Did you take
Yeah,
those?
this one's a composite, but the pictures that I used were both taken at about the same time with the same equipment. I just took a background picture and then overlaid a shot of the moon on top of it.
Okay, those are nice. Can you send me those?
Yeah, sure.
Thank you.
Do you want me to, or do you want to put like your email in the Zoom, or?
Oh yeah, I'll do that. Sure.
All right.
Okay, so very good. Let me do this first before I forget. Okay. Okay. Good job. I like how you utilized different techniques for trying to find ages, and they were all relative ages, right? You weren't telling me absolute dates. So that's good. On the flip side, they weren't used exactly correctly. But that's okay. That's just these little things that you pick up along the way. So you talked about superposition, and you gave a great example of that, where that crater is overlapping the rill in that third image. But even just in general, talking about craters in craters, that's superposition. And one thing I'm going to say before I forget, this is actually for both for both of you. Watch the amount of text you have in a slide, especially if you're going to basically wind up saying those words in your presentation. Having them on the slide, people will start reading them, and that means they stop paying attention to you. So that's why you certainly have text near you, to look to refer to if you need to while you're presenting. But I would really save your slides for imagery, tables, and of course, after you do your research, you'll probably have tables, or you might have some sort of plots to show. You're annotating your images. That's marking them up with letters and stuff. That's good. That's great. That way people can see what you're talking about. Very simply can coordinate what you're talking about with the image. So go back to the very first image. Okay, yeah, so everything you see here is an impact crater. One question for you was, did you consider those could have been a different kind of feature?
I considered if some of them were formed from volcanic activity, but I don't believe any of them were.
Okay, what made you think that, and then what made you decide they weren't?
From the research that I did with all the readings, the way that they described the volcanic craters and those kinds of features, they didn't really match up with what I was looking at in this image.
Okay. What piece of information that I will admit I withheld in every picture, what piece of information would have been really useful to help you make that distinction right away?
If maybe like if we had an example of one of those other kinds of craters.
Okay. But what about what you can already see in the image? It's not a trick question, just asking. I don't know if the readings really covered this, now that I think about it. So if I had given you the sun, the direction the sun was coming from, then you would know where shadows should be.
Okay.
Depending on whether you have a depression or a relief, like a hill or a volcanic hill. So if I told you the sun was coming from the left, then you probably could have been like, oh, well, yeah, those are all craters. But no, okay, so they are. But what you did do was you talked about like how filled in the crater looked or its lack of a defined rim, that's really good. That's a great argument that you made for talking about the relative ages of these things, and saying that I'm going to compare these. You did that right up front, so that was good. So I didn't have to spend my time trying to figure out which ones you're comparing. So in using crater counting, though, crater counting is something that's done to, it's actually done to find an absolute age for a surface. So for example, if you were to take this image and you wanted to find it's relatively absolute, but if you took this image and you took another image of the moon that had the exact same square area, okay, you count all the craters that you see in those two images, in each image, and the size, and you record the sizes of all the craters in those images, and you compare the two, you can plot them on this thing that's called an R plot. And that can give you an estimate of the age of that surface. So not necessarily the craters you see, but of the surface in general. So that's how crater counting is used. Because the only samples we have that we know come from the surface of an object are from the moon. But even those are from wherever they picked them up, right? So anyway, so crater counting, yes, that's used to find relative, almost absolute ages, but more used, but they're used for finding relative ages of a surface, and not of a given size, of a given area. Like usually they're things like 100 square meters, or maybe even like 100 square kilometers, something like that. They're big areas that they usually look at. But because of images like this that we get from LRO, those areas that they can actually now see craters are much smaller. So crater counting is being done, as I understand, on images like this in smaller areas, because we can now see these craters that we couldn't before at this scale. So yeah, this is all be basaltic. It's all part of a mare. You found the Apollo 12 site, the Surveyor 3 site. Most people do not catch that. In fact, my team the other day, so do you know what that linear thing is extending away from Apollo 12 lander?
Like
they're at the top
here, or
yeah, that and going to the left of the lander. Do you know what that is? What those are?
I don't think Apollo 12 had one of the rovers, because I don't think they were used that early in the Apollo program, but footprints, I guess. So
yeah. So they're the footprints. Those are astronaut footprints. They didn't have the rover, but they did have like a two-wheeled cart that they could put tools in and pull behind them. So that's kind of a combination of their footprints and the wheels from that cart. And Alan Bean walked over to the Surveyor 3 and pulled a piece of it off, and they brought it back. Study the effects of sitting out there in space for a couple of years and what that did to the metal. Okay, so let's see. Okay, that's it for that image. So let's go on to the second one. This image is really difficult to analyze because the sun angle is very high in this. It's almost straight overhead. So if you were to look at this image in this area at a different sun angle, those craters would look a lot more round than they do. You'd probably see a few more of them, and it'd be a lot easier to measure their diameters. But I like how you use the scale bar that I gave you to come up with diameters. It's very good. Nobody, I think, has ever done that. If they did, they didn't tell me that's what they did. But that is a real, as you say. And yes, this is a zoomed in area on image 3. So go ahead and go to that image. Yeah. So yes, it's that that bow or that bend up there at the top. in that image. Apollo 15 did land near here. That's correct. Just a little bit to the right of that bend. They did have a rover, first mission with a rover. They took it over to the edge of the rill. Took some images. If you haven't seen them, look up Apollo 15 images from Hadley Rill. It's a lot bigger than you might think it is.
Yeah, as you were saying that, I was
it's
thinking I gotta look
big.
those up.
So this is a sinuous rill, so it's not a straight rill. But I saw where you were going with that. So we do find straight rills very often along the margins of mare. So right where this would be. I mean, it's mare, it's a dark area, it's right along the highlands. But in this case, we're looking at a sinuous rill that formed in the mare that was already present.
Okay.
But you are correct that the crater, Hadley crater, is younger than Hadley Rill, for the reason you stated. That's very obvious. So yes, that's a mountain. Those are part of the Lunar Highlands. And what are the Lunar Highlands in general?
They're like mountain ranges, I think. I don't remember it being that clear in what I read. But
so yeah, like in this image, yes, you would look at this and call it a mountain range. There are some areas where there are no mare, and so all you see is this white material, or it's not really white, it's brighter material. The highlands in general are the original crust of the moon. So when the moon solidified after formation, there was a time where the moon was just this ball of this bright material. There were no mare. And then over time, the mare formed after the large impacts, after the that weakened the surface enough so that then eventually later on, magma forced its way through the surface and filled in those low-lying areas, some of those low-lying areas. So let's do a quick, not a superposition, but a relative age dating thing here. So between the mare, the highlands, like for example, you have labeled C, the mare, the highlands, Hadley Rill, and Hadley Crater. Can you label them just out loud for me, oldest to youngest?
So oldest would be the highlands, then the mare, then the Ryle, and then crater.
Yeah, exactly. Yep. Very good. Oh yeah, and you were talking about that little crater D. It's kind of elongated, kind of looks like a peanut.
Oh yeah.
So yeah, that could be from a very low impact. It certainly could be. Do you know what else it might be from? It's an impact, but not necessarily a low angle.
Maybe like a rubble pile that hit it. So not something that's like really defined and in one piece, but like kind of broken up.
Yeah. So it could have been, I mean, I can't tell here. It could have been maybe 3, 4 different meteorites. Maybe, it could have been a single meteorite that maybe got broken up somewhere on the way to the moon. Maybe it passed by the Earth relatively close and it broke up into these 3 pieces and it boom, 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 hit it and made this chain. I don't know. But yeah, but it could also be from a very low impact or low angle impact. And in the image above that, yeah, that little one, yeah, it's relatively new because, like as you said, the ejecta is still pretty well defined. Okay. All right. Very good. One thing I would also recommend you look up if you haven't done this or if you haven't seen it before. Have you seen the Apollo 15? It's a video taken during the mission. It's their the hammer and feather experiment.
Yeah.
Have you seen that? Okay, good. Good. I'm not gonna worry about having you go look it up. It's pretty cool. I think Apollo 15 is one of my favorite missions. I just love the geology. There's so much geology in the area. That video I absolutely love. Dave Scott's one of the last remaining Apollo astronauts still around. There's only like 3 or 4 of them, I think. So anyway, all right. Well, okay, so you're done with this. Good job.